All right, so we're going to be looking at the 2021 BC FRQs. We're only going to look at the BC ones. So I've got all of the whole document loaded here, but question number one is both AB and BC. So if you want to look at the solution, you can watch the video on the AB YouTube page. But question two is BC only. This is calculator active since it's question two. And what we know is that we are calling the position of a particle, and it's not just moving in a line, it's moving both horizontally and vertically. So we're going to have a position vector of x of t, y of t, and the velocity vector. Keep in mind, it's really easy to read this incorrectly. This is x prime of t. I don't know if you can tell my x prime. And this is y prime of t. And easy to see the word position and to just link it with that, but this is the velocity vector. And we also have an initial position at time 0. So for part A, we want to find the speed. So in AB, if something's moving along a straight line, speed is the absolute value of velocity. But if we're looking at moving both horizontally and vertically, then speed would be x prime, specifically at 1.2 quantity squared, plus y prime, specifically at 1.2 quantity squared, and then make sure you square root all of that. And it is actually challenging sometimes to put this in the calculator. Now what I'm going to do, I already defined these. I'm going to call the velocity of x f and the velocity of g y. And so I did this earlier and I did it wrong because I took a derivative of the velocity again. I realized it and had to restart my video. So because I didn't want you guys to see a wrong solution. But I'm going to take the square root, and I already have my velocity for x already defined as f. So I'm just going to go ahead and evaluate f at 1.2 and square it. And then plus the same thing, I'm putting those extra parentheses here, whoops. And oh wow, really having trouble here. Try again, there we go. G, which is already the derivative of y, because that's how I inputted it. So notice f is the derivative of x, g is the derivative of y. These are already derivatives. You don't want to take a derivative again like I tried to do up there. That was wrong. And then I'm going to square that. And that's going to give me my speed at 1.2. So 1.271. You can go to more decimal places. You just cannot go to fewer. And if you were using that answer, again, if this were not the final answer in part A, then you should round that to 5 decimal places at a bare minimum. That's all the work you need to show. Part B, we want to find the total distance traveled by the particle. And so total distance traveled is kind of an interesting idea on this problem because we have to understand that this is arc length. So we've got to read this properly as this is arc length. Okay, so in AB, total distance is the definite integral of the absolute value of the velocity. But for moving in more than one direction, both horizontally and vertically, we do arc length. So I will do the definite integral. We're going from 0 to 1.2 of the square root of x prime of t. Make sure that is not evaluated there. This needs to be t, and y prime of t, quantity squared. And notice I did name this x prime and y prime up in the problem, which is, I think, helpful for the reader to make sure they know what I'm doing. Although they would understand that since we called the position x and y, they would interpret that correctly even if I didn't write that. Okay, so I'm going to do the definite integral. So shift plus from 0 to 1.2 of the square root. So basically arc length is the definite integral of speed. Just make sure that you do this in terms of t. And notice this is already a derivative. Okay, this is already, f is already the velocity function for x, as g is already the velocity function for y. And I get 1.00982. You can write that how you want. If you're like, I don't like trying to round that with the 9.8, certainly you could write it all the way out. You can truncate it. You could round it. Now, if you round this, don't write it like that. You would write it 10. You still need those 3 decimal places because this didn't actually terminate. I would say just leave it, be happy, and walk away. All right, point C. We want to find the coordinates at which the particle is the farthest to the left when t is greater than 0. Explain why there's no point at which the particle is farthest to the right. Now, if we're talking about left and right, we're only looking at the x component only. Okay, we're only looking at the x components. We're not going to be looking at the y components at all. And so when it says farthest to the left, what that's actually looking for is we're looking for the absolute min for x of t. And when you're looking for an absolute min, you want to look at the critical values. So I'm going to set x prime of t equal to 0 and solve this. Now I want to show you some things that can be concerning a little bit about solving some of these. So by the way, you can kind of look at this and probably set that equal to 0 and guess what that would be. But I'm going to use the calculator. I'm going to show you what kind of happens sometimes with the solve function. Is that students forget the notation, so I'll just run through that again with you. So we're solving, we're f of t, because that's, oops, I need a space, I guess. Oh, there we go. So I want where f of t is equal to 0, and then I'm going to solve this for t. Oh, I think I'm supposed to put solve not outside the parentheses. I think that's why my calculator was mad at me. There we go. Let's try that. And I get t is 1. Now, by the way, when I get this t is equal to 1, I will tell you I don't use solve ever if it has a trig function. I use the graphing calculator and look for zeros instead. And that's because the graphing calculator is going to give you a better view of which answers and not going to write them in a periodic form. So just kind of FYI, I don't use solve for these. Okay, now this is going to happen when t is equal to 0. Or t is equal to 1 is when we have a critical value. Now, is that for sure going to be the absolute extrema? Normally we would want to do endpoints, but I don't really have endpoints here. So I am going to use more of an alt table to kind of pursue this idea. Now time they said was greater than 0 always. So I'm going to split this up and just see if I can get a sense of what's happening here. And so I'm going to evaluate x prime and see if that tells me if the particle is moving to the left or the right for x. And so I could evaluate x prime with my calculator really easy. So I'll do like f of, I don't know, 0.5. And all I really care about is it positive or is it negative? I'm getting a negative here for that value. So I am moving to the left. So if we kind of imagine my start, wherever I'm starting at the point at -2 at time 0. Okay, here's where I'm starting. And I'm going to move to the left until I get to time 1. I don't know how far it is. I haven't bothered to find that. And then after that, let's see what happens with the velocity after that. So I'll do like 1.5 or whatever, anything bigger than 1, and I can see that those are switching over to a positive. So after that, I'm moving to the right. So after that, I'm turning and I'm moving to the right, and I'm moving to the right forever. So I am moving to the farthest to the left. I have to explain why. They will not look at my table. They will not look at my diagram either. So I'm going to put this as the only time the particle changes from moving left to right. Or changes at all. I'll just say changes direction horizontally. Maybe I think that's better. Thus, it is furthest to the left. At t equals 1. Now let me make sure that I found what they wanted me to find there. They said, ooh, find the coordinates of the point. Okay, so I'm not done there. I did figure out that it's going to happen at 1, but I need to find out the coordinates of the point at 1. So I need to find out where x is at 1 and also where y is at 1. Well, I'm going to use the accumulation model. They did tell us where x is at 0. And so if I do the definite integral from 0 to 1 of x prime, which I'm calling f, and I add that to that initial value of x, that initial value of x is -2. So this will be -2 plus whatever that definite integral is. this is going to tell me the x component. So I'll have -2 plus, and then I'll do my definite integral going from 0 to 1, because I only want to stop at time 1. I'm starting at time 0, of the derivative of the x component, which I called f. Okay, that was my velocity for x. All right, so it looks like my x coordinate is -2.0 or -2.60, either 3 or 4, whichever you want. And the y component, I'm going to do the same way. I'm going to take y at time 0, and I'm using the accumulation model again from 0 to 1 of y prime of t. So y at time 0 is 5. Oops, didn't need to move my document. There we go. So this will be 5 plus the definite integral from 0 to 1 of y prime of t dt. So 5 plus the definite integral from 0 to 1 of y prime. Oops, not sure what happened there. Y prime I called g. And I'm getting 5.410. Okay, so that's going to be at the point at time t equals 1, which is at -2.604 and 5.410. That was part of what they wanted me to do. They also said, explain why there is no point where the particle is farthest to the right. Well, at t equals 1, the particle turns and moves to the right for basically forever. It never turns back and moves to the left. Therefore, there is no max value. Or how did they say it? I'll just rephrase it. There is no point farthest to the right. It's going to go forever to the right. You might find a way to say that better than I did. But we need to talk about the fact that it's never turning back, or it's always moving to the right from that point on. And that alt table was helpful to see that, because this wasn't on a definite closed interval, so I really couldn't test endpoints. I needed to find a different way to explain this, so I need to be looking at the signs of the derivative to help with that. All right. Question number 3 was on both A, B, and B, C. So if you want to see the worked out solutions for that one, you can go to the A-B video, and we've got those solutions worked out for you. Question 4 was also both A-B and B-C. And so again, you can see this on the A-B video. All right, question number 5. This one is a BC only question. It is not calculator active because of the fact that it is question number 5. Only 1 and 2 are calculator active. So y equals f is the solution for this differential equation. I think it's worth our attention to notice that x, the variable in the denominator, is our input variable, but this derivative has both y and x. The initial condition is f of 1 is equal to 4, and we also know the second derivative evaluated at 1 is 4. We want to write the second degree Taylor polynomial about x equals 1. Sometimes people skip that, and there is a second part, so we don't want to skip the second part. All right, so to write the second degree Taylor polynomial, I want to start with the constant value of 4, and then I need to find the first derivative, and I will have x minus 1 as part of that. So I'm going to evaluate over here my first derivative, specifically evaluated at the point 1, 4, because we need where x is 1. So this would be 4 for y times 1 times the natural log of 1. Well, the natural log of 1 is 0, so this is 0. So you might go, do I really need to write that? No, but I probably at least initially would, and maybe I'll clean that up for a final answer. And then the second derivative is 4. And so this would be x minus 1 quantity squared over 2 factorial. You could probably leave it like that. I don't think there's anything wrong with that. I think I simplified this because that 0 was bothering me and I was worried I might have to use this later. And so I wrote it like that. Now also on part A, we want to use this to evaluate f of 2. So I'm going to approximate f of 2 by plugging in a 2 here. So this would be 4 plus 4 times 2 minus 1 quantity squared over 2 factorial. And you should just walk away and leave that as your answer. That's the approximate. Now, if you really wanted to, if you're like, I really want to approximate this, go for it. It's going to be 6. But I would just not evaluate it and not risk potentially making a computational error and losing points. Part B, use Euler's method starting at x is 1 with 2 steps of equal size to approximate f of 2. Show the work that leads to your answer. So we're going to start at f of 1. I want to end up at f of 2 with 2 steps, so my intermediate step would be to approximate f of 1.5. But they told us f of 1 is 4. And so that's where I start here, and I want to include the step size. Remember, delta x here is going to be used. So 0.5 times my derivative that I found at 1, which was 0. We found that earlier. And then I would use that output of 4 here. And then I'm going to add on, again, the product of the step size, which is, so 0.5, but times the slope. Times a slope. Now, what slope am I using here? I need the slope when f is 1.5, or at when x is 1.5, which at 1.5, we're approximating the output of 4. So I'm going to use my formula for slope again, which is y, which is 4, times x, which is 1.5, times the natural log of x. Well, I have no way to calculate that, so I'm just going to leave it. 4 times 1.5, if you want, you could calculate that as 6, but you could leave that as a product. So 6 times the natural log of 1.5, you could leave that as your answer. If you wanted, you could simplify that a little bit further. That's totally up to you. It's just, if you'd like to, you can. I think this ends up being 4 plus 3 natural log of 1.5, if I'm remembering correctly. I probably wouldn't risk that, but if you really felt the need. So there's A and B. All right, part C. We want to find the particular solution. All right, we need to understand what this means. When you see this, this means you're likely going to need to separate the variables and integrate. Almost always you're going to have to separate those variables. You should look for that. One way you can tell is, remember, our input variable is x, but in our differential equation here, we have both x and y. And so we need to separate this out. All right, I'm going to multiply both sides by dx and divide both sides by y. And we are going to integrate this, and this is where it gets really interesting. Left side, super easy to integrate. That's the natural log of the absolute value of y, yay. Right side, what the heck? This is integration by parts. This is ultraviolet voodoo. I'm going to think about Lyautey. If there's a log, you let that equal u. The natural log of x is going to be u, and then I'll let dv equal x. So this would be, du would be 1 over x dx, and v would be 1/2 of x squared. So I'm going to do ultraviolet. I like to put the 1/2 x squared in front of natural log. It doesn't really matter. Okay, you might be like, what the heck is happening here? That's about right. All right, and then minus, so ultraviolet minus voodoo. I'll pull the 1/2 out front. I've got x squared times 1 over x dx. So the natural log of the absolute value y, I'm not going to mess with that yet. I'm just going to do this integration. So this is really going to simplify to minus 1/2 the integral of x. Okay, if you simplify that. So if I use power rule here again, I'm going to raise the power of 1 to the power of 2 and divide by that. I also have that 1/2 in the front, and this is plus c. And this is plus c. Now I'm going to exponentialize both sides here. So on the right-hand side, that's y. On the left-hand side, c comes out front as a multiplier. Everything else is going to stay a power. And now I'm going to use my initial value. I would exponentialize before you use the initial value because the absolute value of y can give you a false solution here. all right? And remember, the absolute value goes away once you exponentialize, because when you exponentialize, you only get all positives anyway. So that's why we leave that. Okay, the initial condition is 1, 4. So I'll put in 4 for y and 1 in for x. So this is 1/2 times 1 squared times the natural log of 1, which is 0, minus 1/4 times 1 squared. So this is 4 is equal to CE. Let's see, this all zeroes out. So e to the power of negative 1/4. Well, I want to divide by that to get c alone. So this is 4 over e to the negative 1/4, which that kind of looks weird. You could leave it like that, but I'd write it as 4 times e to the power of 1/4. Just move that up to numerator. And then I'm going to go back up to here to write my final answer. So 4e to the 1/4 times e to the 1/2 x squared natural log of x minus 1/4 x squared. Now you could leave it like that. Nothing wrong with that answer. If you want to get the answer that's more likely to be on the scoring guideline, although they would accept this, this is fine. Since we have the same base of e, we can add those powers together. So I would probably suspect, although we haven't seen the scoring guidelines yet, that it would probably look more like this. Either are fantastic answers. All right, so that's number 5. Let's take a look at our last one, which is number 6. Oops. Here we go. This one's a BC only question. And this is our question on Unit 3, Infinite Series. So you can anticipate BC often has a question on Unit 2 with particle motion and parametrics, maybe polars. And then they usually have a question on Taylor polynomials. And then they usually have a question that will be on Unit 6. And this sometimes they kind of merge together, or Unit 3, pardon me, on series. And you can see this one's going to kind of merge together. So G has derivatives of all orders. The Maclaurin series for G is given by blah on its interval of convergence. We want to state the conditions necessary for the integral test. Ooh, and then we have to use it. The conditions. Sometimes students forget that the integral test has conditions. The conditions are that as we're doing this, when we're using it for 1 over e to the n, is that 1 over e to the n needs to be positive, which it is. E to the n is always positive. Decreasing, which it will be if we increase our values of n. And continuous, which it is. It will never equal 0 on the denominator. Those are the conditions for the integral test. Those need to be stated. And then use it to show that this converges. So I'll do the limit. And we're doing this from 0 to infinity. So you can pick any variable. College Board usually picks B. I usually pick A. Just difference, I guess, in the training. And I'm doing from 0 to A of 1 over e to the n, which I'll write as e to the negative n dn, just because it's easier to integrate that way. So keep that limit notation there. They will mark you down if you remove that limit notation or just completely forget about it. So e to the n is its own integral, but negative n has a derivative of negative 1. I need to divide by that. So this would be negative e to the negative n evaluated at a and 0. So this would be the limit as a approaches infinity of negative. E to the negative n would be 1 over e to whatever power, so I'll plug in an a. And 1 over e to the power of 0. Now that I have a actually written in here, I can stop writing the limit notation. If I put an infinity here, this would be negative 0 minus 1, which is 1, which is an actual answer, and therefore it converges. So as you get a finite number there, you are good, and that converges for part A. All right, part B, we want to use the limit comparison test. So we want to compare. And they even tell us what we're comparing it to show that this other series converges absolutely. Well, remember, when things converge absolutely, we want to verify that they converge with the alternating, and then we also want to verify that they would converge without the alternating. So I want to look at both. So I'm going to run out of space here. I'll see if I can squeeze this in here. You would have plenty more room on the actual exam. All right, so looking at, I'm going to call this S. So for S, it's alternating. The terms decrease in magnitude. Oh, wait, maybe they already told us it converges. No, okay. The terms decrease in magnitude and the limit of the non-alternating part as n approaches infinity, which would be 1 over 2 e to the n plus 3 is indeed equal to 0. So S converges. All right, let's see what happens when I look at the absolute value of this. They said to use the limit comparison test. Well, the limit comparison test is the limit as n approaches infinity of the initial one without the negative, without the alternating part. There is no absolute value here, by the way. Times, or actually divided by the one you're comparing it to. Okay, and so we are going to compare this to 1 over e to the n. All right. Now, when I come to compare it with something, I do need to show what's happening with 1 over e to the n. We already know that this one converges by the integral test. We did that in A. We don't need to redo that. Okay, but when you're using a comparison test, you've got to know what's happening with the one you're comparing it to. Now I want to divide by the one I'm comparing it to, so instead I'll multiply by its reciprocal. So this would be the limit as n approaches infinity of e to the n over 2e to the n plus 3. Well, we could think of these as essentially these guys are basically having the exact same rate of change since they're both e to the n. And so I'm just going to make this a ratio of the leading coefficients, which is 1/2. This is positive and finite. You must say that. Therefore, this also converges. So my final conclusion is S converges absolutely, or is absolutely convergent, however you want to phrase that. There's my final answer. All right, now I want to determine the radius of convergence. Well, we determine the radius of convergence for this by using the ratio test. So I'm going to use the ratio test here for this one. So the ratio test for part C says we're going to take the limit as n approaches infinity. Ratio test uses the absolute value. Limit comparison test does not. And it says it needs to be less than 1. And so that's part of what we're doing here. So I'm going to ignore the alternating part because I'm doing the absolute value. So I'm going to not deal with the negative 1 to the power of n. So you do absolute value, that goes away. So I'll have x to the n over 2e to the n plus 3. And then I want to divide this by n plus 1. Oops, sorry. I start off with n plus 1. Let's fix that. And then I divide it by the original expression. So I'll multiply by the reciprocal of the original expression. All right, let's simplify this. So this would be the limit as n approaches infinity of the absolute value of, let's see, we would have only one x left, and times 2e to the n over 2e to the n plus 1 plus 3. Well, I'm going to take out the absolute value of x, and I'll evaluate the limit of what's left. So let's take a look at this. The plus 3 does nothing. The plus 3 does nothing. It goes away. Okay, as we approach infinity. But you see I have one more n on the denominator? One more e to the n. If I reduce 2e to the n over 2e to the n plus 1, the 2's cancel out, and I have 1 over e. So the absolute value of x is then less than e. Now, they didn't want the interval. They just wanted the radius. So the radius is e. Remember, this is a Maclaurin one, so it's centered at 0. All right, part D. The first two series of this term are used to approximate g of 1. Use the alternating series bound to determine an upper bound on the error. Okay, so I'm going to start, this says to start at 0, so I'm going to plug in a 0 to get the first term. If I plug in a 0 on the top, I get 1. I plug in a 0 on the bottom, I get 2 plus 3, which is 5. For the next term, I'm expecting this to alternate, should be a negative, but I'll plug in a 1. So this is if n equals 0. Now I'll plug in if n equals 1. And I get negative 1 over 2e plus 3. This would be what we would be approximating it with. Now, the error for this would come from the next term. the absolute value of the next term. That's how alternating series bound errors work. So the error, if I now plug in a 2, if I plug in a 2, I get a 1 on the numerator. On the denominator, I get 2e squared plus 3. And so my upper bound, and it's already positive, so I don't really need the absolute value, but no one's going to be mad at you, for the error is 1 over 2e squared plus 3 for my final answer. And that is the end of the 2021 FRQs.